Okay, welcome to the lecture on climate change. As always, I have listed some goals and objectives. I'm not going to go through these. I'm going to try to move. There's a lot of material on this on climate change, but I know that it can get a little bit kind of bogged down. So I'm going to try to go rather quickly through this with the understanding that you can go back and replay to make sense of these and pause, and you'll have access to these slides. Please do take note that we have videos on Keeling Curve and sea level rise that are interactive, so please take time to explore those. And then here is our planetary boundary, with climate change being a boundary, a key boundary here, and that we have, now this is the 2023 planetary boundaries figure, with climate change being separated into carbon dioxide concentration for the first time and radiative forcing. In other words, what is the carbon dioxide in parts per million in the atmosphere as one of the aspects we can measure of climate change, and what is the total radiative forcing of all of the greenhouse gases that are moving into the atmosphere and warming up the atmosphere. So here's just a brief view. Hopefully by now you've watched the videos and done the interactive assignment on climate and understanding climate and how that works. And so just to review here, we have a bunch of different aspects. We have the sun's energy output, which tends to be pretty constant over time. This is just showing us, about 100 years of data. But we have the sun's energy output, and we talked about insolation, and we talked about how on thousands of years cycles you might see differences in things like Milankovitch cycles, but over short time periods those are irrelevant. And then we have land use changes. We have aerosols, right? And so aerosols being this particulate matter suspended in the atmosphere. Oh, sorry, the aerosols from urban pollution are in purple, and the aerosols from volcanic venting, those are spiked because volcanoes erupt, and that's when you have big aerosols going into the atmosphere. As we know, those have a cooling effect, and the heat trapping greenhouse gases will have a warming effect. Hopefully that's pretty clear as to how that works chemically from now in terms of trapping and re-radiating radiation from the sun. So why do scientists believe that current climate change is anthropogenic in nature? In other words, anthropogenic means caused by human activity, so human caused. And this would be to distinguish it from this idea of natural climate fluctuations, which, as we talked about, would be primarily due to things like Milankovitch cycles or massive disturbances. So something like you may have heard about a meteor hitting the Earth that would have caused a dramatic climate shift for the dinosaurs, or events like that, right? But otherwise, in our current time period, we believe that this is anthropogenic climate change. So remember the carbon cycle. Take a quick look here. The carbon cycle, we have a natural, carbon will move into the ocean. It would become embedded as part of the sea floor. Things die and they move further down, and they could become fossil fuels. And then, of course, anything that we do that has some sort of combustion reaction or burning of a carbon product is going to put carbon dioxide in the atmosphere. And then other things will be putting some of the other greenhouse gases that we'll talk about in a minute into the atmosphere. So this is our carbon cycle. And then, of course, we have a fast carbon cycle happening between photosynthesis and respiration, and then a slow carbon cycle that happens over millions, hundreds to millions of years. Occasionally you get volcanic eruptions, and I have a nice little data here showing that volcanic eruptions and release from the carbon dioxide from the slow carbon cycle into the atmosphere, you would expect somewhere between 130 and 300 million metric tons of carbon dioxide per year, whereas humans are emitting a huge magnitude larger than that. And all of this is really taking things that are deeply deposited into the earth and our fossil fuels and burning those and putting them into the atmosphere. And then I talked a little bit about this in some other videos, but then we get some feedbacks between land use changes, snow ice melt, permafrost emission releases, and so you get these what we call positive feedback loops that are kind of pushing the climate spiraling in one direction or another. So, global surface change. This is from the IPCC report, that is the Intergovernmental Panel on Climate Change, the 2021 updated report. The initial report came out in 2010, and there have been periodic updates since then. And one of the more recent updates was really looking at the specificity of what we can expect with different changes in climate, in total surface temperature. The initial report looked primarily at simulations of different potential carbon futures, and that was to get some conversations going at an international scale about a 2 degrees, you might have heard of a 2 degrees Celsius target, and a lot of that was related to the IPCC initial report. And one of the discussions that was had at these intergovernmental panels was quite a few nations were concerned about how viable their lives would be with 2 degrees Celsius if that were the target. And so they asked these experts to go back and revisit and look at 1.5 degrees, or what the different simulations were. And this report actually really highlighted quite a few of the dangers of a 1.5 degree Celsius change. And quite a bit of that made the news about 5 years ago, a little under when this came out. There was a lot of news that was a bit depressing, talking sort of about the world ending in 2030 were some of the headlines. Now, that's not the message I'm going to give you here. That is a journals translating, news reporting translating some pieces of the evidence that are here about how we should be concerned, but maybe not quite so alarmist. Okay. So what are we looking at here? Here we're looking at, so now, by now you know what a climate proxy is. You should understand from those wonderful websites that I pointed to you towards how we can reconstruct climate over hundreds of thousands to even millions of years, depending on the type of proxies that we're using, and how this can help us understand what the temperature is in the atmosphere. And so when we look at this, here's one example, right? Looking at reconstructed climate over time. And then we have very good records from the last 150 years. And in the video talked about, how the closer you get to the present, the better your records are. And then of course, we've been capturing, measuring carbon dioxide and temperature in the atmosphere pretty steadily for the last almost 100 years now. So, we have this unprecedented warming, right? So this is a you're looking at a change in temperature from the normal. So we're looking at 1 degree Celsius, right? Change over the last 100 years. And we've seen that, and then we'll talk about some models there in a minute that kind of verify this. And then the scientists, of course, trying to understand all the factors here, say, okay, well, what if it was just solar and volcanic energy? What would we expect the change to look like, versus if we consider these human land use changes and carbon and atmospheric changes, right? And so if we remove these from a model, right, and we just look at these factors, we would not see the kind of warming that we've actually experienced, right? The kind of warming we've actually experienced matches a model that includes both human and natural phenomenon of our observed changes. Okay, so here again, we're looking at observed warming, right? So observed warming relative to 1815 to 1900. So again, we've seen about a 1 degree temperature change. And then what are the contributions to that, right? So human influences, greenhouse gas influences, other human drivers. Note some of those, because of human aerosol pollution, would actually would have a cooling effect. So the warming effect is despite that. And you can see here sulfur dioxide here being something that would have a cooling effect, et cetera. So here we're looking actually at what our greenhouse gases are, and I have our carbon dioxide, our methane, our nitrous oxide. And then there's other ones as well that are greenhouse gases, right? But we do focus primarily on these guys right here that have a high parts per million in the atmosphere and a high radiative forcing potential, which just means that they can get really warm when they are heated up. Okay, so what are the anthropogenic sources of the greenhouse gases? Why do we have these in the atmosphere? Well, first of all, by now you should understand that these are naturally in the atmosphere. We have greenhouse gases. So our greenhouse gases are coming from all kinds of sources. And again, just to remind us that they are naturally in the atmosphere and they form a blanket over the earth that does form a useful warmth for our atmosphere, and it allows planet Earth to be habitable. However, human activity on the planet has created an imbalance of the amount of greenhouse gases that are in the atmosphere. So where are these things coming from? Methane, or natural gas, that is CH4, that will come from anything that is decomposing. It could also come from us harvesting natural gas and using it for energy purposes if it escapes. But typically when we use it for an energy purpose, we burn it, and that breaks it down into carbon dioxide and waters. But otherwise it can go directly into the atmosphere from decomposition. And one way that humans, landfills is an obvious one, but things you might not think of is some of our land system changes, such as wetland changes, or causing permafrost melting has caused an increase of methane that was trapped in permafrost to go into the atmosphere. Carbon dioxide can come from deforestation, particularly when you're burning the trees that are being deforested. It can also come from any fossil fuel use. So I'll have any fossil fuel that is being burned that will put carbon dioxide into the atmosphere, because a combustion reaction is a carbon that is being burned. It gives off light and heat, and it releases carbon dioxide and water. So whenever we're using fossil fuels for transportation or energy, that's going to put carbon dioxide into the atmosphere. Methane can also come directly from animals on farms and agriculture. Carbon dioxide and nitrous oxide can come directly off of our mechanized agriculture and high fertilizer input agriculture processes. And then our factories are going to be putting things like nitrous oxide, carbon dioxide, and chlorofluorocarbons, which are all greenhouse gases, into the atmosphere. So as I think you can just sort of imagine, every day, you could look at what you do on a daily basis. Every time you turn on a light, if that's not coming from a solar panel, it's probably getting a fossil fuel burned to get that light energy to you. When you drive a car, even if you have an electric car, indirectly that electricity probably was created by fossil fuels. So all day long, we're doing lots of things that are putting carbon dioxide into the atmosphere, and that is all coming from mostly carbon products such as fossil fuels that have been stored for millions of years in the earth. So here we're just a little bit of a, from 2010, so a little outdated, but a nice little metric of where humanity's carbon dioxide comes from. So things like fossil fuels and cement and land use change are big factors, and then where it goes. And this is a nice little reminder that some of it returns to Earth, and that's why trees, we call them carbon sinks. They absorb carbon, right, in their process of photosynthesis, and they give off oxygen in exchange and create sugar for the rest of the ecosystem. So trees are a really important carbon sink. And then some of it's going into the oceans. That will be important when we talk about ocean acidification. And then some of it is ending up in the atmosphere, right? So just note here, we actually have less carbon dioxide in the atmosphere than maybe we should, just based on the amount that we're burning, because some of it is ending up in other places. See, over the years, you have carbon dioxide, methane, nitrous oxide, all on this exponential growth curve since about our Industrial Revolution. And none of this at this point should be surprising, right? That we have had an exponential increase in these greenhouse gases, and that's, again, all related to how industry is subsidized by energy. I'd like to point out here this question of what country emits the most carbon dioxide. We have a lot of conversations at a global scale about kind of finger pointing and blaming other countries, and I'm not going to do anything to stop my carbon emissions until this country does something. So there's this wonderful website where, for those of you who have slides, you can click on the slide and it will take you to the website where you can see it will allow you to sort of play around with what is our current carbon map of the world. So the larger circles are bigger emitters. And as you can see here, the United States, China, and India, as maybe you're expecting, are the leaders of total amount of, this is metric tons of carbon dioxide, right, per year. However, if we look at this a little differently, and we change it to kilograms of carbon dioxide divided by GDP. So thinking about carbon dioxide as a function of economic output, that map shifts. And that's a relevant thing for us all to think about because of the conversations we've been having about the relationship between energy, fossil fuels, and GDP. If we look at this again, right, and now we think about it carbon dioxide per person, well, now it's rebalanced again, right? And I think carbon dioxide per person, if we kind of think of the world as having a carbon budget, if every person was allowed access to a certain amount of carbon dioxide emitting activities to subsidize their lifestyle, right? Who is really benefiting and who's really not? So this map really lets us sort of think about who benefits from climate change, or who's really not benefiting from climate change, but benefiting from the activities that are leading to climate change. Whereas sometimes we hear conversations about nations feeling like they're victims of climate change, and this map would help us sort of think about why they might feel that way. The Keeling curve is a really great source of data. So it is named after the last name of the scientist who started constructing this curve. And so this question here, what does it tell us about climate change? So carbon dioxide has been measured at a Mauna Loa observatory in Hawaii for, well, since the 1950s. So as you can see here, this is, once again, you can click on this, you can click on the slide and it will take you to the Scripps Oceanography website that allows you to look a little bit more at this data. But this has been taken for the last, again, for these last approximately 50, it's been taken for a minute, 40, 65 years. I knew I could get there. And what you can see here is this oscillation in carbon dioxide concentration in the atmosphere throughout the year, steadily increasing over time until you get to the present day of 2025. Why is it oscillating? Because of those trees we were talking about. So the most of the land mass on the Earth is in the northern hemisphere. So at the end of the summer in the northern hemisphere, around September, if I'm not mistaken, is where the valley is in this crest. That's when we've maximized carbon drawdown for the year. And then 6 months later, we have the highest carbon dioxide in the atmosphere because we have the least amount of primary productivity on the planet at that time. So that's why those are going up and down throughout the year. And you can see in faint blue that there's a trend line in the middle showing this steady increase in carbon dioxide. So here, I just got a little bit of a larger screenshot here of this website where you can see that the latest carbon dioxide reading, that's pretty high, right? So 427.58 parts per million. Keep in mind, I'm looking at this. I took this down and I didn't double check when this reading came from, but it is July here. So we would expect this to be, you know, on the slight decrease if we're going to hit a valley in September before it heads back up. So back to our 350 parts per million goal in the initial planetary boundaries, right, in our planetary boundaries. And when we looked at the paper from 2009. I'm going off the top of my head here, but I seem to remember that it was around 380 at that point. So in the last 2009 to present, we're looking at 16. In the last 16 years, it has really skyrocketed. So it seems that we are not moving in the direction that scientists are suggesting we may want to move. Okay, so I would really like you to, I put this up here, and again, you have access to these slides. This is a complicated figure. I would like you to spend some time thinking through. I'm not going to walk through all of it here, right? But this is this idea of radiative forcing, right? So radiative forcing, how much energy, that other piece of the climate puzzle of what scientists are trying to measure, right? How much energy is being trapped and re-radiated to heat the atmosphere by these different factors, right? So again, we're looking at things like carbon dioxide, we're looking at methane, we're looking at nitrous oxide, our halocarbons, et cetera, et cetera. So you can understand, right? And then our aerosols, we've mentioned in class before that we would expect that to have a cooling effect, so forcing in the other direction. And then total anthropogenic radiative forcing relative to 1750. So we're just seeing an increase in this radiative forcing throughout time. All of this leading scientists to believe, back to that initial question, that climate change is primarily anthropogenic in nature or human caused and really caused by these carbon dioxide emissions. Again, this is, it's fairly basic chemistry thing that's understood. Hopefully there's that very cool video about looking at how carbon dioxide heats up a jar. And so it's not terribly complicated science of what we're looking at here to draw these connections. And I really like to always highlight this because often the same people who will rely on a weather app won't want to talk about climate change. And you can trust me, your weather app is much more complicated science than understanding greenhouse gases and radiative forcing. So have we seen changes in the temperature? Okay, so I'm going to break this one down here because I think it's important. This is again from the IPCC 2021 report. And so we can now look at what are the observed changes we've seen in different parts of the globe. So it's not just that there's been 1 degree Celsius everywhere across the globe. We have areas that have already experienced more like it's hard to match these colors, but I'm going to go maybe a 2.5 degrees Celsius change up at the poles. And that's because heat tends to radiate towards the poles as it moves across. And we looked at some slides, some climate slides on that. And so you have an unequal heating, unequal distribution of that heat on the planet. And this is what we've actually experienced. So this is coming from data that has been taken and modeled on the planet, right? This is a simulated change. So without getting into the nuts and bolts of modeling, and frankly, I don't know exactly how they did these models, but I know a bit about modeling, you need to use, so you can create a model, right, of how we expect the different parameters to behave, okay? And then you can run the model and see what it says will happen with 1 degree Celsius warming, how that should be distributed across the globe based on the parameters in your model. And then you can compare that to what has actually happened. And this is important because you can see here, this basically says, oh, that's a pretty good model, right? And they're going to have data tables and sensitivity analyses that really get into the nitty-gritty of whether or not this is a reliable model. But just showing it, looking at it here, you get the, and these are the best scientists in the world producing this, you get the idea that these are pretty good, like there's a pretty good match between the simulation they're running and what we're able to see, what we've experienced on the planet. Why is that important? Because then they ran the simulation for future models. So they basically came up with as good of a model as they possibly could and then looked at the future. And they took that model and they looked at the future, and this is what they're expecting to happen at 1.5 degrees Celsius warming. Remember that whole point that I made about sort of this updated focus. And we're seeing that at 1.5, we're expecting maybe some rather catastrophic conditions in the Arctic. In terms of, that would be 4 degrees Celsius change, which in Fahrenheit you could that you can do the math. It's times 9 divided by 5 plus 32. And so you're going to see some pretty big changes in certain regions on the globe. And then at 2 degrees Celsius, remember, this has been the target of these big intergovernmental discussions, such as the Paris Accords. The target that they couldn't successfully agree upon was this guy, saying, hey, what if we tried to limit it to 2 degrees? And then finally, this would maybe be a worst case scenario of 4 degree Celsius global warming. And at that point, we would probably expect that there would be some sorts of catastrophic collapses that would really kind of, let's say, keep human ability to kind of prevent or adapt with ease to these changes. It would really limit the options that we have. Okay, so what types of impacts are we already seeing from climate change? So this is an interesting figure. I've got a couple different ones of these. This is, again, same report. So what they were showing here, this is showing heat extremes. And so we're seeing particularly quite a few heat extremes on the globe, and fairly high confidence based on their models that these are caused by human contribution to climate change. Okay, so this heat extreme is one of the major weather extremes that and I think a lot of us can sort of, yeah, we can kind of see this, right? We're getting every year new record heats, new record heat waves, people struggling to adjust to these heat waves, deaths associated with them. And so this is one thing we're already experiencing, and we would expect it to get worse in the future. Heavy precipitation. So huge impact of climate is changes in precipitation. The tricky thing about it is precipitation. Remember, I mentioned that weather app. We all get mad when we don't know where the rain's going to fall and when. This is right. So it's a tricky thing to try. Precipitation is tricky to model, particularly when it comes to where that precipitation is going to fall, where and when, where the drought is going to occur. And I bring this up because one thing we do know for sure is the increase in size of storms is bigger with climate change. And that's just, again, it's kind of simple science. The water is able to evaporate. There's more water evaporating with a higher temperature. Makes sense. We all can observe that with some pretty basic experiments. So more water evaporates with a higher temperature, and more water can be held in the atmosphere with a higher temperature. But water can only stay in the atmosphere for so long before it gets heavy and falls out. So a major impact of climate change is heavy precipitation, because there's just more water up there, and when it rains, it pours. I have walked in on a million conversations where I hear people just talking about this all the time. Oh, these storms, they come through so fast now. So as an anthropologist, when you hear these kinds of conversations, it feels like, I'm hearing lived experiences of climate change in action. We can think about things like Hurricane Helene being 400 miles apart. The size of that storm, not necessarily the strength, but just the sheer size of it and the amount of moisture that was in the atmosphere is certainly linked to a warming ocean and a warming temperature in the atmosphere. So thinking about this going forward, we would expect increased events of heavy precipitation. But again, when a particular event or the particular things people are experiencing, there's sometimes limited agreement on how these current events are linked fully to climate change. But the trend we're certainly seeing heading in one direction. And then this is just the concept of drought being the opposite of what I just talked about. Unfortunately, when it rains, it pours, and then it won't rain for a really long time. And that's one of the things. Our agriculture depends on consistent rain and predictable rain, and those things have become more difficult. So, climate futures. What might we expect going into the future? These are simulations in annual mean precipitation change. Right, so we looked at some of the heat changes. Well, we would expect changes in precipitation too, right? So look at this extreme possibility, right? We're seeing severe drought in some places and just downpours in places where you would not expect rain, right? And so these are potential future changes based on, but again, very difficult to sort of know exactly with all the feedback factors exactly how that will play out. Sea level rise. Okay, so again, they know worst case scenario, unlikely, right? Low likelihood. However, right, one of the things we see is with warming oceans, warm things expand, right? So if you have a warmer ocean, it's going to expand and actually get bigger. We can probably all relate to this, right? You work out, you get sweaty, and then, well, you might have trouble removing a ring that you have on your finger, right? So warm things expand, and the oceans know, the ocean is the same. When the ocean, when it gets warm, it expands, and that is the main contributor to sea level rise. You could also look at things like melting land ice, okay, but not actually the melting sea ice. That's a confusion there, because if you think of ice melting in a glass, that won't expand the water in your glass. However, expanding, warming oceans, expanding those oceans is contributing to sea level rise. And one thing I think people don't understand about this is, yes, it's slow, right? You can see this is meters, right? So it's slow, but if you're an island nation at sea level, it might really change your experience of the next storm that comes through. Or if you are Florida, right, that is already converted marsh. Saw an amazing map the other day of those of us who have forgotten what Florida was like at the time that the settlers arrived. The marsh was drained essentially to make it a livable place, which means that most of the state is actually at sea level. And so now with just a small change, you're already starting to see increases in flooding, particularly in relation to storms. And then I bring this up only because we will be talking about ocean acidification. So that carbon dioxide going into the ocean is causing something we will call, we're going to talk about down the road, called ocean acidification. One thing I forgot to mention, but again, and you've taken a look at these papers, the IPCC report, these are just different simulations, right? Different climate futures. And I think it's kind of clear. Worst case scenario, best case scenario, right? And again, these kinds of reports are intended to help guide policy at an international scale as they're made by international climate experts.